1989 E3. This year they decided to make the circuit the third problem, and they've given us a battery, a resistor, and a capacitor all in series, and they've given us numbers for these, and they look like nice and pretty numbers. So for part A, we're going to charge up the capacitor, and when we're done charging the capacitor, all of the voltage of the battery is going to be reflected as all of the voltage of the capacitor. So once it's all charged, when we go around the loop, we're going to have the voltage of the battery brings us up. There's not going to be any current. And then there's going to be the voltage of the capacitor to bring us back to the ground safely, and we'll be at 0. So the voltage of the capacitor is going to be equal to the voltage of the battery. They didn't ask that. They answered for the energy stored. Well, we can use that fact to calculate the energy stored in the capacitor by doing 1/2 C, which is 6 micro, times V, which is 20, and then you square it, which gets us 1.2 millijoules, because this is 10 to the minus 6, and then when you square 20, you get 400, and 400 times half of 6 is going to be 1200, so 1200 times 10 to the minus 6 is going to get us 10 to the minus third. All right, part B. Now that we've gotten our minds around this circuit, they're going to change the rules on us. Now we're going to increase the spacing between the plates. Well, how much work is going to have to be done? Well, that's going to be related to the change in the voltage. So for part B, it looks like the charge is not going to change there. So if we say charge original equals charge final, then that means CV equals C prime V prime. And they said we're increasing it to 4 times its value. That means C prime is going to be 1/4 the capacitance as it was originally. And that means our new voltage is going to be 4 times the original voltage if we're going to keep the same charge on there. So the work done is going to be a change in the potential energy of those charges that are sitting on there. So it'll be Q, and we're going to go from whoops, hang on a second. We're dealing with a capacitor here, so we can't just do QV. We have to do 1/2 CV squared. So this guy is going to be 1/2 C prime V prime squared minus 1/2 CV squared. And this guy is 1/4 the original guy, but this guy is 4 times, and then you're going to square it. So once we've done that, we have the work is equal to 3 1/2 CV squared, because we're going to have 1/2 and the 1/2 and the C and the C and the, wait, that's 16V squared, so that'll be 4. So this will be 4 times 1/2 CV squared minus 1/2 CV squared. That's where we get this 3 of 1/2 CV squared. Well, what was the original 1/2 CV squared? That was 1.2 millijoules. So the work that's going to need to be done is going to be 3 times that, or 3.6 millijoules. All right, part C, the current in the resistor immediately after. Well, we just went from a voltage to 4 times the voltage. Doing that is going to produce some current in the resistor. So V equals IR, and jumping to 4 times the voltage of the battery, I, and then the resistance is 300,000. That's going to get us a current of 2 times 10 to the minus 4th amps. Now, once we've yanked around the capacitor, we're going to let it sit there for a couple of seconds and see what happens after the fact. Now that we've done that, how much charge has moved? Well, we can figure out how much charge was on there originally by doing 6 micro times 20. That gets us 120 microcoulombs. And then when we yank it, so that's the original, and then here's the final. And then once we yank it to make the capacitance, the distance between the plates, which makes the capacitance different, that's going to be, let's see here, that'll be C over 4, but then for voltage. Nope, wait a second, sorry. That 4 shouldn't be there because we're still attached to the battery. The battery's still going to demand to be 20 volts. So at the end, this is going to be Q final. It's going to be 30 microcoulombs. So what we're doing here is we have this set up and we let it reach equilibrium. That's in part A. And the capacitor is brought up to 20 volts by the battery. And then in parts B and C, we mess with the capacitor and we do it really, really fast. And what that does is it makes the capacitor momentarily 80 volts here, which is going to force the charges back into the battery, but the battery is set at 20 volts. So this 80 volts is finally going to come back down to 20 volts because that's how much the battery is. And the battery is setting the final voltages here. That's what the battery is doing. So that momentary 80 volts is going to slowly decrease back to 20 volts. Now, in order to have 20 volts on there again, how much charge you need to have? You need to have 30 microcoulombs of charge given the new capacitance. So how much charge got pushed back into the battery is essentially what they're asking, but they don't want to say pushed back into the battery because that'll give the game away. We subtract these two guys and we get 90 microcoulombs. And in part E, they sort of give it away. They say how much energy has been added to the battery. Now we've added energy to the battery, but we haven't changed the voltage of the battery. The battery is stuck at 20 volts. So for part E, and I'm going to have to get rid of this so that I have some space down here. So part E, the energy added to the battery is going to be QV. So we've put energy back into the battery. Notice that the equation that I'm using for potential energy is different here. This is Q times V, and this is 1/2 CV squared. This is because this is a capacitor, and this is a battery. So 90 microcoulombs were added back to the battery, and they were added at 20 volts because that's what the battery is. So this is going to be 1.8 millijoules of energy was added back into the battery. All right, so it spent 1.2 millijoules. We had to do, oh, I erased it, 3.6 millijoules to mess with things, and now we've added 1.8 back in. Well, these numbers don't match up, and the 3.6 numbers don't match up, and that is because through this entire time, every time the charges have moved, we've lost energy in the resistor. Some of the energy from the battery, or going to the battery, has been lost to the resistor. That's why the 1.2 and the 3.6 and the 1.8 don't and are not going to match up.